Hello everyone. Today we're going to be looking at Chapter 2, Differentiation. We will be looking at Section 2-1, the derivative and the tangent line problem. So as I usually start with a little recap of the things we have done earlier and what we're going to do in this session. So in the last chapter, we talked about tangent line problems and limits. Then we also solved limits using numerical, graphical, and analytical approaches. In this lecture, we're going to be looking at slope of the tangent line to a curve at a point and how it is used as the derivative of a function. And we'll also be using the limit definition to find the derivative of a function. And finally, understand the relationship between differentiability and continuity. So a little recap for our tangent line problem. This is the classic calculus problem that is given a function and a point, and this function can be any function like a curve. If it's a straight line, awesome, we can know how to find the equation of that line. But if this function is a curve, then the main question in calculus was, how do we find this equation of the tangent line to the graph at a point, say, P? And what we found was that limit was the key which helped us to figure it out. And remember, to find the equation of a tangent line, at a point P is basically equivalent to finding the slope of the tangent line, because you're already given a point. So what you really need is the slope of that tangent line. And the way we went about was we just took an arbitrary curve. So this black one, is your curve, y equals fx here, suppose. This is the curve y equals f of x. And you had given a point P, and you want to find the equation of the tangent line at this point P. So what did we do was we picked up another point Q, and then draw a line through this, which is a secant line. And then there was this point Q. We could have drawn many points on this curve and then just draw secant lines. What we found was that as these different Q's were approaching the point P, the slopes of the secant line were exactly approaching the slope of the tangent line at P. So what we literally said that the slope of the tangent line to the graph of this function at the point P is said to be the limit of the slope of the secant lines. Remember, there are many Q's on the curve. And as you pick up a Q very close to the point P and you draw a secant line, that slope of the secant line is very, very close to the slope of the tangent line at P. So now we're going to come to this definition of a tangent line with the slope. Once again, we're going to go back to the things we had defined in Chapter 1, but we're just going to give a little new name here. We say if a function f is defined in an open interval containing C, and if this limit of delta x approaches 0 of delta y over delta x, this delta y is the change in y over the change in x, which is f of c plus delta x minus f of c over delta x. Now it says if this limit exists, and we are going to call it M, then the line which passes through the points C and f of c with slope M is nothing but the tangent line to the graph of the function at the point C and f of c. Let me just quickly draw a curve once again here for you. So here, this is my curve, and we want to find the equation of the tangent line at the point P. What did we do? So we want to find this equation of the tangent line. Okay, what we did was we looked at different Q's over here. The nicer graph is in the previous slide, so Q1, Q2. You could have a point here too, Q3, and we just basically drew lines. And then we said that this limit, and we talked that the limit, so this one, delta y over delta x, remember this is the point P, this is the change in y and change in x, these are, and when we say delta x approaches 0, much more nicer picture is this is the delta x. That means as these point Q's are coming closer to P, these are the delta x's. So that means this difference, or the change in x, is coming very, very small. It's that which we denote by delta x approaches 0. That's what we do. Delta x approaches 0. So this distance I'm talking about, guys. Okay, so this one is basically the slope of all, the secant lines. And as the slope, this change in x of these different secant lines becomes small and small and small, which is looking in terms of the limit. So we say slope of the tangent line is said to be the slope of the secant lines. And that's what the representation is about. This representation, guys, where I'm just circling around here with this green thing, this is basically all this written in simple mathematical notation. This whole line is basically this. Okay, so coming back to what we were talking here, let me erase this one here so that okay, so if this limit exists, then what we say here is that the line which passes through the point C and f of C. Now this is the point P, which is the C. This is the point which has C and f of C at the coordinates with slope m. So this tangent line is basically this is the slope. So we say if the line passing through this with slope m is the tangent line to the graph of this function at this point. So basically if this limit exists, this is basically the slope. That's what we are saying. The limit, which is this, the black line over here, this is basically the slope of the tangent line. And the slope of the tangent line is given by this formula. Okay, the limit here. Okay, so the last line, the slope of the tangent line to the graph of this function, f at this point, is also called the slope of the graph of the function at x equals c. So we have done a lot of little theory here. Now let's start with examples to understand what we have to look at here. Okay, so let's start with this example. Now remember the thing, if I have to find the slope of a tangent line to the graph of the function at a point, I basically will be using this definition. Okay, so that's what the next example is. It says, find the slope of the graph of the function fx given by 2x minus 3 when c is 2. Now this is what we have learned in our previous slide, but let's just talk about the things we already know. Now let's look at this line given to us. Fx equals 2x minus 3. Clearly, if you notice on this right hand side of the slide here, this is a straight line. And we all know by looking at the equation that the slope of the straight line is basically a 2. Okay, so this is a 2. Now what we're going to do is, it doesn't matter what point we're going to look at on this line. Any point we pick up on this straight line, the slope is always going to be a 2. We know that. Now we're going to prove it with the help of the definition we just learned. Remember what we said, that if you want to find the slope of a graph of any function at a point C, so C over here is 2. So this is the formula we have to apply. This is the formula, okay, where your C is given to you. Now I just have to plug in, and then it's simply evaluating the function at that point and then just going ahead and just doing a little algebras here. Okay, so let's start. So the limit is delta x approaches 0. C, remember, is your 2. 2 plus delta x, that is f evaluated at 2 plus delta x minus f of 2 divided by delta x. Basically, I am just substituting in place of c the 2 because that's what we are asking. Okay, now after this, the limit is your calculus part, but this rational function, the numerator and the denominator here, the numerator basically is evaluating the function at the specific points. That's your pre-calculus or algebra, if you remember from there. So here it is, f evaluated at 2 plus delta x. Now remember, what is my f? My f is this, 2x minus 3. So in place of x, now we have 2 plus delta x. So now, wherever you see an x on the right-hand side of this function, you replace it by 2 plus delta x. So that's what I have done in the numerator. 2 times 2 plus delta x minus 3, kept it in square brackets, negative. Then it is 2x minus 3. Now this one, f of 2. So remember your x here is 2 times 2 minus 3. Because you're evaluating at 2. Remember this one. So wherever you see an x, you replace by 2. So this is here, it means x is 2. So it's 2 times 2 minus 3. Okay, now simple computation. Now take the 2 inside, it's 4 plus 2 delta x minus 3. And then take the negative inside, it is negative 4 plus 3. And when you cancel out, same terms with negative signs, so you are left with 2 delta x over delta x. You remember negative 3, negative 4, and 3 and 4 cancel out. So now this limit of delta x approaches 0 of 2 delta x over delta x is common. And then limit as delta x approaches 0 is 2, and it is 2. We already knew that. This is an equation of it's a straight line. And a straight line will always have slope in this for this function to be a 2. And we also have got it by our definition when we applied it to solving this problem. Now let's take up a graph of a non-linear function. In other words, we're going to have a curve. So that's the next slide we're going to look at. So here it says, find the slope of the graph of this function fx equals x squared plus 1 at 2 points 0 and 1, minus 1 and 2. So this is the point 0, 1. This means this is the point. Your 0, guys, is c here. And this is f of c. So c is 0, f of 0 is 1. In this one, your c is minus 1 and your f of c is a 2. Okay. Now to solve this problem, if I have to do it using the one I did in the previous slide, then I will have to do it twice because I have two different c's. What we're going to do is we're going to make our life simple. We will just keep the formula, and we will just use c. We will not change it to 0 or minus 1. We will just go ahead and do the whole computation and taking this function, and at the very end we will just substitute the values. Okay, so that way we can save a lot of time. Okay, now let's come for, we know the slope of the graph. So we want to find the slope of the graph. We already know it's a parabola. And looking at the graph, we would see when you're coming from the left-hand side, on the left-hand side of the y-axis, you see the graph is going down. So if you draw a tangent line anywhere here, it's going to have a negative slope because the lines are going down. And if you're looking at the tip, the vertex of this parabola, if you draw a line, it's a horizontal line. And we already know the horizontal line has slope 0. And if you're going on the right-hand side of to the y-axis and above the x-axis, the graph is going up. So if I draw any point over here on this one, the tangent lines, if I draw any tangent lines here, all these tangent lines, remember, are going to have positive slopes. Okay, I'm not able to get this right here. Okay, so now let's go ahead and just apply the formula. And as I said, because we are asked to find the slopes at 2 different points, what I'm going to do is I'm just going to go ahead and won't put the c's in terms of the numbers, just go ahead and solve it like that, and then in the very end we will change the values in c. So remember, this one is the first limit is basically the definition. So when we find the slope is given by this. This is the m, which is the slope of the graph of this function. Now what are we going to do? We are just going to go ahead and replace. Now we're going to just work on the rational function, which is here next to the limit, and basically focus on the numerator part. The first thing is we're looking at f of c plus delta x. Now that means evaluate the function at c plus delta x. What's the function? X squared plus 1. So just go ahead, replace your x by c plus delta x, and then you have c plus delta x the whole square plus 1 minus f of c, which is c squared plus 1. And then just simple computation. Here's the squaring formula, c squared plus delta x squared plus 2c delta x plus 1. And then you distribute the negative inside c squared plus 1. You get negative c squared negative 1. And then just, cancel out the common terms. So negative c squared 1 and negative 1, they basically, and c squared, they cancel out. And what are we left with? We are left with delta x squared plus 2c delta x divided by delta x. Now, clearly on the numerator, the delta x is common, and now we have delta x plus 2c, and we can easily cancel out the delta x's. What are we left with? Limit delta x approaches 0 of delta x plus 2c. So wherever you see delta x plus 0, so your final limit or the slope of this graph in a general form is simply 2c. So let's look at what is the slope at this point. So what is the slope at point 0 and 1? The formula gives m is the slope is 2c. Now remember, your c is 0. This is your c. So what is it now? 2 times 0 is 0. And that also makes sense because this is the point which is the vertex of the parabola. And you draw a horizontal tangent line, which actually is a horizontal line. And we all know that the slope of a horizontal line is 0. So this is totally right. So this limit of slope of this, the definition of the slope of the graph of this function exactly is in sync with what we already know. Okay, let's look at the slope at the point -1 and 2. Now remember the formula. The slope is given by m equals, according to what we just did, is 2c. Remember your c is -1, guys, here. So it is 2 times -1, which is -2. That slope is -2. When the slope is negative, that means the tangent line should go down. And that exactly is what you are looking from the graphical point of view too. Okay. Now let's look at a vertical tangent line. Now the definition of a vertical tangent line, the definition of the tangent line we just have talked about is not covering the possibility of a vertical tangent line. For a vertical tangent line, we have to have a little slighter definition. It says if a function f is continuous at c, okay, then the limit, remember the slope, we are talking about the slopes, that is the slope, the limit delta x approaches 0 of f of c plus delta x minus f of c over delta x is either positive infinity or negative infinity. Then the vertical line x equal to c, which passes through this point, is a vertical tangent line to the graph of f. Be very, very careful that this positive and negative infinity does not mean, remember in the section 1.5, we talked about infinite limits. We said, oh, that means there's going to be a vertical asymptote. Now, vertical asymptote and vertical tangent lines are two different things. And the biggest difference is here. When you look at the graph of this is a vertical tangent line. A vertical tangent line will be touching the graph of the function, whereas a vertical asymptote, guys, remember, never touches the graph of the function. So that is the biggest difference between a vertical tangent line and a vertical asymptote. So whenever we see the word vertical tangent line, it means that the line will touch the graph of the function. And in terms of solving it, what you're going to see is that first of all, the function has to be continuous, and the limit delta x approaches 0 of that f of c plus delta x minus fc over delta x is positive or negative infinity. Okay, so just to keep in mind, remember that vertical tangent line is different. I'm just going to write in capital letters. It is different than vertical asymptote. So when you think of the word vertical asymptote, okay, let me even, use a different. This is a vertical asymptote, guys. When you see a dotted line, and that is a vertical dotted line, and then you see the graph, suppose the graph goes like this. This graph is never ever going to touch that vertical asymptote. That's the biggest difference, guys. A tangent line you see over here, it is going to touch the graph of the function, whereas the vertical asymptote, the vertical line x equals c, will never ever touch the graph of the function. So please be very, very vigilant. Okay, coming back to the derivative of the function, because this chapter is differentiation. Okay, once again, it is going back to what we have just done. We are just going to give it a new name. Remember, we said that the limit is delta x approaches 0 of f of x plus, or c, I'm replacing the c here, is f of c plus delta x minus f of x over delta x. Now, this we said was the slope. Let me just show it to you again here. Don't want to get you confused, but it is the same thing. Remember this one? We're looking at the graph of the tangent line, and we had at a point. Now this c could be x. Remember, it's just a variable. This, that, and that's what we're doing is now we're saying this thing, this limit, which was saying the slope of the tangent line to a curve at a point, is called the differential of the function. That's what we're simply doing. It's the same thing. We're just giving a new name to it. Just remember that. Okay, let's come back here. So the derivative of a function at a point, at x, this is the point x and f of x. So the derivative of a function at x, so that means now I'm looking at the point P as x and f of x. That's it. It's like any point on the curve. Is defined as f prime of x equals limit delta x approaches 0 of f of x plus delta x minus fx divided by delta x, provided the limit exists. Now remember, this is what we were also going was the slope, which was that's how we started. This was the slope of the tangent line to the graph of the function at a point P. So I'm saying my point P has these coordinates, x and f of x. That's it, nothing else. Okay, so remember this f prime, guys. Remember, it's a function. This is a function. Okay, f prime is a function of x. Very, very important that the derivative of a function is a function itself. Now, there are various notations for it. So if I say my function is f of x, the derivative is f prime of x. If I say it is y, y prime. Y, we can write this as dy by dx. Fx as dfx over dx. These are various notations of the derivative of the function. Now, let's do an example. We will simply if I say find the derivative. Now here the question says find the derivative of this function using the limit process. Basically applying this That's the definition. Okay, so if I say find the derivative of a function using the limit process, that's how we will be doing. Here the only difference is, oh, this should be an x, guys. This should be an x, a little typo. Okay, so f prime of x is limit delta x approaches 0 of f of x plus delta x minus fx over delta x. Now remember, now your function is a square root function. We have to just go ahead and root x plus delta x minus square root x over delta x. Now notice, if I want to take the limit, remember the derivative means the limit exists. So if I look at this function, it's a 0 by 0 function. Remember the indeterminate form? Now, and also if it has square roots, if you remember from chapter 1, we can get rid of the square root by multiplying by the square root of x plus delta x plus square root x and dividing by the same thing. So what happens is you're applying the difference of squares. So a minus b and a plus b. So when you do that, so now it's all computation. The limit keeps on happening, and we here on the in this problem. So it's x plus delta x minus x divided by delta x times x plus delta x square root of that plus square root of x. Clearly the x's and minus x cancel out, and then in the next step, the delta x is common, so we take that out. So now the second last step, you see limit delta x approaches 0 of 1 over square root x plus delta x plus square root x. Now clearly that this limit is existing, there's going to be no issues, and we just substitute. It's direct substitution, if you remember. It's 1 over 2 root x. Okay. Now this is important that remember this x, as it is going to be in the denominator and the limit has to exist, that means function is existing, this x cannot be 0 here. Otherwise this will not work, remember. Okay. So that is how do you, basically this is like how initially it used to be done, and in the the limit process, it's a lot of computation, guys, which we definitely need to understand. So it's a limit, it's a little practice for you, and on that, as I would make, as I normally do in the class, is I would give you some problems. So I would like you to work definitely and practice these problems. These are some of the questions with this practice, it will help you get ready for your exams and quizzes and stuff like that. Okay. So here is so definitely please practice these problems. It will help you out. Then the other thing we are going to talk about is the relationship between differentiability and continuity. It's a very, very important concept. And that here we are saying is if a function is differentiable at a point, then automatically it is continuous. It's a very important concept. So what it says is differentiability implies continuity. But if we go backwards, like if I say my function is continuous, it may or may not be differentiable. A very classic example is the absolute value function. Okay. I'm going to explain it with the help of graph, why a function fails to be a derivative. We're not going to take the analytical approach here. So what we're going to say is, okay, let's look at how do we make a distinction. A function is differentiable and a function is not differentiable. There are two scenarios for a function to be not differentiable. If your graph has a sharp turn, remember what we just said in the previous slide. We said that if a function is, an absolute value function is an example of a function being continuous but not differentiable. So notice, this is my absolute value function. Clearly it is continuous. Once I, on the graph, I'm just going to be remaining on the graph. I'll never come out of it. But it says it is not differentiable. And the reason is this. Because of a sharp turn. This is sharp point or turn. This is not differentiable because the left-hand derivative is not the same as the right-hand derivative. Let's look at this one. Just look at, you remember what's a derivative? Derivative is basically the slope of the tangent line at any point. Now, this is an absolute value function. The slope, there are two straight lines, you know. And it's a piecewise function also, if you remember, absolute value function. When I'm coming from the left-hand side, the slope is -1, and I'm coming from the right-hand side, the slope is 1. Remember, this slope is the right-hand derivative. Because remember what we just said, that the slope of the tangent line to the graph of the function is the derivative of the function. We just said that. Here, let me go back and talk about this one here. This is a very, very important concept. That this derivative of a function is nothing but the slope of the tangent line to the graph of the function at a point. So keeping that in perspective, we find that just looking from the graph, this has a different slope, this has a different slope. If the slopes are different, remember the derivative is the limit. Keep that in mind. So when we say f prime of x, what is it? It is the limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x. That's a limit. And when we say the limit exists, and we say the f, that means this limit exists. That's what we say. When we say the limit exists, that means the right-hand limit and the left-hand limits, they should be the same. And specifically at this point, there is going to be an issue. Here, any point, the left and the right are going to be the same. But at 2, that's the problem we will have. So the limit at 2, if you're coming from the right hand side, it is +1. From the left hand side, it is -1. So the limits are not the same. Remember, what you see is here is the graph of the function. But the derivative is basically given by the slope of the tangent line to the curve, and specifically at 2, that's the function is not differentiable. And how do we look at? Just look at from the graph point of view. Oh, there's a sharp turn. That's it. It's done. And the other way the function fails to be a derivative is if you have a vertical tangent line. So there are 2 ways a function is not differentiable: if you see a sharp point or a turn in the graph of the function, or you see the presence of a vertical tangent line. So if any questions are going to be given to you guys in the exams, they are always going to be in a graphical form specifically related to your derivatives for failure of a function to be derivatives. Okay, so let's look at this one. So let's look at these graphs. Are the graphs continuous and differentiable? So just looking at it, clearly this is continuous. These are straight lines. This is a straight line, and this is a piecewise function, but it is still continuous. Remember, if I go, once I'm on the graph, I will always remain on the graph. So all the 3 graphs, this is continuous, this is continuous, and this is continuous. Now let's look at the first graph in terms of differentiability. There are no sharp points. So this one is differentiable. Similarly, the second graph is also differentiable. It's a horizontal tangent line. Now, we just said, if you see a sharp turn, you have a sharp turn at 4. So this one, the last graph, is not differentiable. And the reason is, it has a sharp turn or a point or whatever you want to say. Okay, let's look at another graph. Is this graph continuous? Yes, this graph is continuous as well as it is differentiable. Remember, this is a graph of a squaring function. It's basically fx equals x squared. So this is differentiable as well as continuous. You don't see a sharp point. It's a nice little movement of the curve. Okay, so this one graph is continuous and differentiable. Okay, so the last thing, guys, you're going to do is practice. So there are 3 graphs given to you, and figure out which one is continuous and differentiable or which is not continuous and differentiable. Thank you.